Welcome to 20th lecture, stability of structure. Please note that previous lecture I wrongly wrote 19th, 18th, but it would be 19th. Okay. So what let us briefly recall what we were discussing. So we were discussing part of dynamic instability. So the one we were focusing on the aerodynamic instability in bridges, and then we have taken the example of collapse of Tacoma Bridge in Washington State, 1940 that happened, right? Because at that time it was the knowledge on aerodynamic instability was not matured actually, people are not, and it was not incorporated in design. Okay. So we started discussing on this topic. So we have this, this was a cable suspension bridge, and then we consider a reduced order model for this bridge, and that kind of model we also use when we test it in wind tunnel. Okay. Always, even though we have good predictive model, but we always want to do numerical physical modeling, experimental modeling, and test it wind tunnel to check its critical velocity for flutter. Okay. So there we use sectional model. Okay. We consider a beam model with equivalent property scaled. Okay. And those are referred as aeroelastic model. Okay. With the distributed elasticity. Okay. And other. Anyway, so with the this simple model for this structure was bridge structure was taken as a simply supported beam. Okay. And then the respective property of the section was also obtained, EI and GJ. GJ is the EI is the flexural flexural rigidity, and GJ is basically the torsion rigidity. J is the St. Venant constant, right? Warping will be very negligible here. And then there is difference between inertial axis and the elastic axis. That distance we considered as y, and then we have introduced several Flutter derivative, right? Out of all this Flutter derivative, only two will be remaining. This Flutter derivative is nothing but they help in expressing the aerodynamic loading that is coming on the structure as a function of the displacement, as a function of the response of the structure, right? And all this Flutter derivative we have to find out through experimental investigation or a computational fluid dynamic simulation involving fluid structure interaction. Okay. Out of all, so here there was 2 degrees of Flutter model. So it involved the vertical deflection of the deck as well as torsion. We denote as W and theta. Out of all this Flutter derivative, I have written down the equation of motion, and then you have seen out of all the Flutter derivative except these 2 remains, all other vanishes, and these are expressed as a function of reduced frequency, which is width of the deck, and then frequency of oscillation, and V is the wind velocity. We have considered the average wind speed. Okay. We didn't consider fluctuating part of that. Okay. Of course, that will have some influence or some influence on that, but the mean speed if we consider, and what is the critical value of this mean average speed of wind that will trigger instability, that will be sufficient for the design, because we want to design it in a way so that the critical velocity for the fluid triggering fluid, that trigger flutter must be above than the design, whatever the speed that wind speed that is that can be realized there. Okay. Now then we consider we had this governing partial differential equation. Okay, 2 simultaneous partial differential equation. So we solved using Galerkin approach, and then we use this kind of approximation, some similar to separation of variable, time dependent part, and then spatial. So spatial one we use some trigonometric function and a combination of trigonometric and algebraic function which satisfies the simply supported kind of boundary condition. Okay. And with all these things, so these are basically denoted as Px and psi x. Okay. And then with all this simplification, what we obtain is the following sets of equation. I have also emphasized that because we have considered a 2 degree of freedom model, vertical deflection and torsion, just to make the system little low dimension. We would have considered the lateral deflection as well, but that we didn't consider. And if we consider lateral dimension, it will unnecessarily increase the dimensionality of the problem. I mean, increase the number of Flutter derivative from 8 to 18. Okay, that's what you. So then I will write the matrix equation. If you can recall, it will be mu I2 mu y I3 mu y I have defined, and this is Im I5. Please note that Im is the mass moment of inertia, right? And these are integral. Rest of the thing w double dot 0, theta double dot 0, and then plus here we have written Cw plus 0.2 pi rho capital B I2, and then this is 0, and here it is 0, and then here it is C theta plus 0.05 pi rho capital B cube 2 minus V by FB I5, and here it is W0 theta dot theta 0 dot plus EI 100 minus GJI 554 W and theta is equal to 0, 0. And all these I1, I2, I3, I5 are nothing but some integral I1, I2, I3, I4 and I5. These integrals I have written in the previous class, and I will just express one of them. These are nothing what you obtain by integrating the stress, these approximation functions which we used for the displacement field. Phi x, this derivative is space derivative and dot is time derivative, and similarly all other, please note that for I3, so here it is psi x and phi x dx, okay, and so on, okay. All these things I have noted in the previous class. So what we can clearly see here, that you see that the aerodynamic loading essentially got incorporated into the damping term. Right hand side is a homogeneous system of equation. So these were like damping from with material terms, right? This damping, which is viscous damping, that comes, okay. But additionally, because of this aerodynamics, the effectively, because the force that is being exerted on the deck by the fluid structure interaction is expressed in terms of response of the structure, right? So it is the damping that is coming. So effectively they are contributing in damping, okay. So that become a function of the velocity of the wind, the speed of the wind, and the rho, of course, density of the air, and then B is the width of the deck. What we can see that this, the one which is associated aerodynamic damping associated with the flexural mode, it's always positive, but this one has potential to be negative because it involves 2 minus B by B term, right? So because for some value of E it will be negative, and that will reduce the damping, and it will contribute in negative damping, that will trigger instability. You understand that? So ultimately when you come there, then of course we will write it now in simplified form. Well, this is the nothing but mass matrix. I will write it like that, mass matrix, and maybe I will write this, maybe U double dot plus C U dot and plus K U is equal to 0. This is a homogeneous system of equation, right? Homogeneous system of equation, and this leads to what? This is an eigenvalue problem, right? This will lead to eigenvalue problem, right? Algebraic eigenvalue problem now, because we have used a Galerkin approach to convert the differential operator into algebraic expression, right? So now you may wonder a little that, well, I mean, how we can convert it into eigenvalue problem, because we can assume u. We can assume u to be as u maybe 0 e to the power lambda t. This kind of solution we can assume. We can assume this kind of solution, right? And then substituting. If we substitute in the equation, then what will you get? You will get, we assume this kind of solution and then substituting this. So substituting, what you will get? U double dot means lambda square, m, right? And then the next one will be lambda c and the last one is k, right? So then here you will get u0 e to the power lambda t must equal to 0. Of course, e to the power for non-trivial solution e to the power lambda t can never be 0 and u0 should never be 0, right? So ultimately this leads to an equation lambda square m plus lambda c plus k, this is 0, right? So this basically leads to a an eigenvalue. So this leads to an eigenvalue problem. We can say this. So this one and 0 must be equal to 0. So this is nothing but an eigenvalue problem, quadratic eigenvalue problem, because this lambda is the eigenvalue. Of course, determinant need to vanish, right? So this leads to a quadratic eigenvalue problem. Why quadratic? Because conventionally the eigenvalue problem we come across there, it is basically quadratic eigenvalue problem, right? Which is little different. The standard form eigenvalue problem, standard form is something like this, right? If you can recall that in for stability class, we have learned like k plus kg u is equal to 0, right? That was the eigenvalue problem that we come across for the static for the buckling, right? That isn't it? That was, and in dynamics, what you have learned is k phi is nothing but omega square m t, right? M t. That is the generalized eigenvalue problem, right? Which you come across in dynamics. In both the cases, you can see that these are first order equation, right? But here lambda is appearing only in the omega square. This is nothing but lambda, okay? But here it is lambda square. That's what is quadratic eigenvalue. Nevertheless, you can convert it into an eigenvalue problem in first order by using state space form. Okay, how can you do that? All of you know the state space form, right? So you can directly solve the quadratic eigenvalue problem, or you can convert it something like this. So that way you convert it. You have, all of you have learned the. Okay, I will come there later. Okay, how? So any nth order differential equation can be converted into a number of first order differential equations, right? Similarly, algebraic, any algebraic expression nth order, they can express n number of first order equation, right? And that's what basically in dynamics it's a always give you the quadratic eigenvalue problem. But you can if you write the equation of motion in state space form, you can convert it into a first order eigenvalue problem. Okay, that all of you are aware about state space form? No. I taught it in dynamics. You forgot complex mode analysis. All of you forgot. That is the problem. Okay. See, m u double dot plus c u dot plus k u is equal to ft, right? Okay, now you can write m, you can write u double dot to be minus m inverse c u dot minus m inverse k u minus m inverse f, right? Now I can define a new state variable. So new state variable. What are the state variable for this? State variable must include the variable which can define the entire motion, completely. So I am defining a state variable which basically contains both u as well as u dot. Do you see that? Even u dot. So now if it is n by n, this is 2n by dimensionality of problem increased, right? But in expense of the reduced order. So then can I write like this? ddt of u dot, ddt of eu, that is eu dot is nothing but what? So here you see that this is 0, this is I, this is minus M inverse K, and here it is minus M inverse C, and here it is 0, it is minus M inverse F. Do you see that? Here the way I have written. Okay. So now, so then so this is nothing but ddt of y dot is AU plus F. Now for the timing, for at least as far as this problem is concerned, we don't consider excitation has been already assimilated in the damping term, in aerodynamic damping. So only these two terms will be there, right? And so this problem can also be written in terms like using a state space form, like, so you can convert a quadratic eigenvalue problem into a first eigenvalue problem of first order, right? Not quadratic. But in that case, the dimensionality of the problem will increase from n to 2n. Understand? So either you form this, either you solve this form or you solve this form, your eigenvalues will be same. Only problem will there will be little change in the eigenvector. But yes, there are equivalents. Understand what I am trying to tell you? And eigenvalues here what we will have, you see that because this is asymmetric, this matrix is asymmetric, right? So eigenvalues will appear in complex conjugate. Eigenvalues lambda will be complex. So when there is complex eigenvalue, they will appear in complex conjugate. So complex conjugate, that means conjugate. Complex conjugate means lambda, any lambda I will be expressed as AI plus I BI, something like that. So real part and imaginary part. Real part can be associated with the damping because it basically acts as an envelope function, right? The imaginary part will be associated with the omega frequency, right? Because e to the power lambda it, that means e to the power ait plus e to the power I bit. So e to the power I bit is nothing but cosine plus psi sine. So that will contribute to oscillatory emission. So bi is associated with the frequency, whereas this ai, the real part, is associated with the damping. You understand what is the role of the real part and what is the role of imaginary part? Imaginary part of the eigenvalues will be associated with the, and you can take square root of that, and taking square root is very simple. For a complex number, to the, anything to the power n, nothing but what? Cos theta plus I theta sin theta to the power n is nothing but cos n theta plus I sin n theta. You know that, right? Euler's formula, right? I don't know, De Moivre's theorem, right? Okay. So you understand that real part of this omega is associated to the damping, and imaginary part associated with the frequency, and from here, and they will appear in complex conjugate plus minus. Clear? We will see that what really happened. So you understand the equivalence between the quadratic eigenvalue problem and then the problem can always be converted into this. Okay. So in MATLAB and all other mathematical software, Mathematica or Mapro, you have standard routine to solve this. So nowadays you do not require to code it. You just call that routine, it will give you. The only thing is that it has, because it appear in complex pair and it is asymmetric matrix, right? You will have a right set of eigenvector and left eigenvector, right eigenvector. Eigenvectors, okay, we are not talking about that, but sometimes there will be left eigenvectors, okay, and right eigenvector, left and right, okay. It's a little different. Anyway, so once you get that, then what will you do? From this case, if we solve this, then we will evaluate it. Now we will do numerical evaluation. So for this, the property of this system will be the properties of the bridge deck for the reduced order 2 degree of freedom model for the Tacoma bridge. The reduced order properties are given. So let me write it down. Span is 853 meter. You see that, almost a kilometer span. B, width of the deck was 11.59. 8, 9 meter, 11 meter, 12, almost 12 meter deck. So it is can easily accommodate what? How many lanes? You see that? And then y, the distance between inertia and the inelastic is 0.01 meter, and moment of area is 80 kg meter. Please note that instead of force, they are expressed. Okay, I mean this is mass moment of inertia. This is m is the m or mu. M is m, or this we also denote as mu, is basically nothing. Mass per unit linear density, that was 8482.67 kg per meter. And then EI, I will write here now. EI is the flexural rigidity. Flexural rigidity is 2.33 into 10 to the power 5. Please note that force is also expressed in some kg. You have to multiply it with G to get it in Newton, right? But that you can do, it's not a problem. GJ, flexure torsional rigidity, is 9.32 into 10 to the power 9 kg per meter cube second square. Do you see that torsional rigidity is significantly higher, right? Here, right? And CW, because it has a lot of, why torsional rigidity is higher? Because it is multiple cell kind of sections, right? That's what, and it is a closed section, that's why. Similarly, CW is nothing but the viscous part of the damping, which is for the in flexural mode. CW is that 50 kg per meter second, and C theta, the viscous part of the damping in the flexural mode, torsional mode, 3.27 into 10 to the power 4 kg meter per second, and density of the air is rho 1.12 kg per meter cube. Okay. So all this property you take and then you substitute in the matrices. If you substitute in the matrix, then you will get mass matrix, you will get damping matrix, you will get stiffness matrix, right? And then you will get the numerical values. Okay. So with all these things, in substituting this, by substituting all these values, substituting, you will get the, and then we solve it. Of course, here we have solved using in MATLAB 2 degree of freedom system. So 2 by 2 matrix is very simple. So you will get 2. How many natural frequencies will be there? 2, right? 2, right? But it's a quadratic eigenvalue parameter, right? Then you will get 4 natural frequencies. But yes, the imaginary part will be identical. Okay. Understand that? Otherwise, if there will be 4 lambda, 4 values will be there, right? Anyway, so you can associate them for the 2 mode, right? So here you can write omega 1 is, in fact, you can separately solve for the to get the natural frequency, you neglect the damping, and you can solve a generalized eigenvalue problem, okay, to get the frequency separately. That also you can do, right? So this one basically by separately, solving we are getting, only including mass and stiffness matrix, okay, without respect to the damping, okay. So omega 1 for the flexural will be 0.0002 radian per second, and omega 2 is 1.2571 radian per second. Could you please tell me which one is the flexural mode and which one is the torsional mode? Which one is flexural, which is in torsional? Which one? Higher one will be torsional, lower one? Come on. So these are the torsions. Torsional mode, right? You people are expert in dynamics. You have done dynamics, you have done advanced dynamics, you are doing earthquake, right? And this is flexural mode. Anyway, so and then you can, if you want, this time period will be what? 2 pi omega, and it is around 5 seconds. I have calculated around 5 seconds. 5 seconds. It is very flexible, right? Even the stiffer one is also flexible, right? Other one is flexible. So now what we will do is See, what we have seen that negative damping can only occur what in torsional mode, right. So, what we will do, flexural mode can never have negative damping. We can find out modal damping for the torsional mode. So, modal damping in torsional mode, how will you find out? See, by solving you can also get respective mode shape. So, there will be two mode shape. So, we are not solving here at least this problem, we are not solving the quadratic eigenvalue problem. I will come there later. First, we are solving the eigenvalue problem, where free vibration problem in the respective mode shape. Okay, with by only the mass and then this. Okay, don't. So the mode shape will I don't know. I didn't calculate. So you will have for the first mode, you will have this for the second mode. Okay, mode shape vector. Or if you want, you can write them as V. Okay, because we have mode shape vector as V, V1, V2. Okay. So this one for the torsional one, or if you want me, so I can write for the torsional, because this is for the flexural, this is for the torsional. This is for the flexural, this is for the torsional. Now modal damping in torsion what? So modal damping in torsional mode. In torsional mode is how much? How will you calculate modal damping in torsional mode? Modal damping in torsional mode, maybe I am writing capital C cap T. So you have a modal, you have the modal, you have the damping matrix C, right? If you want to calculate, so this what? VF transpose VF. This is for F transpose, right? VF transpose. This is how to calculate if we consider, right, modal damping, right. These are uncoupled because off diagonal terms is 0, right. So don't care about the classical and non-classical, but yeah, it's non-classical, right. This is for torsional, yeah, because we are calculating torsional, this eigenvector we should use for the torsional, because we are calculating modal damping in torsional mode, right. Is that fine? Oh, no, sorry. So T and maybe T, another transpose of that, transpose, okay? Then if you do, then you will get a scalar expression for that, because this is matrix and vector. So that, if you do, then you will get an equation, okay? Then get an equation of C, a scalar equation of C, scalar equation in terms of V, right? In terms of V. What kind of equation will that be? We'll get a quadratic equation for V, right? From here, right? Because this V, two expression of V is coming. So then you solve it. So now, so when you get this equation for the, C cap T is 0, to solve it is here, of course, it's a function of wind velocity, right? Wind velocity, and then there will be B and other things, right? 0. So now here you can see that modal damping can go from positive to negative. So from when it is going from positive to negative, when it is crossing 0, can we say that that is our critical velocity that will trigger Flutter? We can do that, right? So you can solve it when it is 0. Solve for VCR. When the modal damping is 0, then find out the respective wind speed for which modal damping for the torsional mode is crossing 0, because after that from positive damping it is going to negative damping, and then it will trigger unbounded response, right. So by solving this, you will get by solving CT is equal to 0, you will get VCR. That critical velocity I am just mentioning to you, that will be 18.77 meter per second, or it is around 50 kilometer per second, around 72 kilometer per hour, okay, 72 kilometer per hour. So when the wind speed is around greater than 72 kilometer per hour, then it will trigger Flutter, unbounded response, because of the negative damping. Clear? So I will just show you, if you solve it little, what really happened. So all of you have followed this till now, whatever I am saying. Okay, one more thing I would like to, if you plot, see there are two way to do this kind of stuff. One is, so when you solve for the lambda, right, if you see all these things whatever we did from our basic understanding of dynamics, okay, we solve for the eigenvalue problem, find out frequency and modal damping, these things. We really don't solve the quadratic eigenvalue problem. But if we, for any other system, see here the system was simple, it's a toy problem, simple system you can solve by hand. If you have a system which has multiple degree of freedom, okay, thousands and thousands degree of freedom, then what will you do? At that time you should have a you should automatize this process, right? Process should be automatic, and there are search algorithm, to search for the respective lambda for which the Flutter instability is triggered. Okay. So how to do that thing, that I am just showing it. Okay. So for that, so you see that lambda k is associated with, lambda e to the power lambda k t, right? And e to the power lambda k is nothing but e to the power, I am writing a k plus I b k t. So e to the power a k t, and then cosine of b k t plus I sine b k t, right? So you see this is the envelope function, which, so what really is happening, you see that, so it will have some kind of, so it is, so that means sine and cosine is basically dictating the fluctuations, right, the periodicity of the solution, whereas this is basically the decay functions, right? You understand that? Decay function. So this is e to the power akt, right? So what I understand, that one part associated with damping, whether other is associated with the frequency. So how to find that out? Okay. So the way we write it, omega k is basically imaginary of lambda k, and xi k, the damping, is minus real part of lambda k and root real part of lambda k square plus imaginary of lambda k square. You see that? This is the frequency and this is the damping. You understand why imaginary part of lambda k is associated with frequency, right? That I have explained. And why damping is like this? Because it is the envelope function. So you now recall a logarithmic decrement, right? Logarithmic decrement, how will you find out, right? Similarly, so in the real part, but then it has to be normalized because it is damping ratio, right? Xi is the damping ratio of the damping to the critical damping. Okay, and if you do this thing, then you will get this thing. So once you get omega k and xi k, for every lambda, you can estimate omega k xi k, right? So for at least for this case, where you have a quadratic eigenvalue problem, you will get 4 eigenvalues. And for the 4 eigenvalue, you will see that that for each mode you will have this xi k and omega k, So now if we plot, here I will be plotting, and then I will try to generalize it, okay. Something like I am not drawing this whole thing, okay. So you will see that this is the way you see that this is xi k, okay, this is xi k. So for different value, this is nothing but wind speed, v, wind speed, huh? wind speed. For increasing wind speed, you see that? So, from positive damping, and this is the damping ratio. The positive damping, it is coming and it is crossing zero damping. What is the value? Zero damping 18 point something, that is what I am for the Tacoma bridge, right? This is the, and after that it is coming to be this, and then it is coming, and then beyond 40 it will be, once again it will go around 1. This is minus 1, that means 100% damping. You see that how damping is changing. So, damping from positive to negative, negative damping as high as 100%. Do you see that? And what will happen to the respective omega? The omega value see here we are plotting the imaginary part of lambda k. So, one positive values that is coming, and another negative value that is coming, and that is basically coalescing. Some coalescence is happening, right? Coalescence of the natural of the frequencies. So, aerodynamic flutter, when it is triggered, the damping is of course being negative, but at the same time that is accompanied by the coalescence of the two frequencies. Do you see that? This frequency is decreasing, and this frequency is increasing, and then this is coalescing. For present case, after that they are occasionally they are both are being 0. 0 means the structure can no more vibrate. It can diverge, because if the omega is 0, that means it cannot, there is no periodic oscillation, it will diverge in one, because with negative damping it will diverge in one side, right? But beyond that there will be negative oscillation. You see that? Even if you come to this regime, fluctuations will be there, but the fluctuation will increase with time, right? So, what will happen? Let me tell you. Under Flutter, what will happen? This will increase. You see that? But when it is 0 frequency, then what will happen? It will increase like this. So, it will increase like this. Please note that here there is no periodic solution. Periodic oscillations are not there. So, this is the case. This is Flutter, aerodynamic Flutter. Whereas these things is called divergence. Now, you have also learned about divergence, where the frequency becomes 0, right? And when that happens, when the geometric stiffness matrix completely erodes the stiffness matrix which is coming from material, right? Contribution of material, right? The stiffness matrix is eroded by geometric stiffness matrix. So, buckling, that is a static instability, is also manifested dynamically in the form of divergence. So, divergence is basically equivalent to the buckling, because essentially its stiffness is all eroded by the geometric stiffness, okay? Because geometric stiffness is being subtracted, and that is what essentially it is happening. You see that these two modes are coalescing, and this is being 0 frequencies, okay? Now, this is happening for this case. Now, for the more generalized case, what really happened, that I will just show it. So, for the more generalized case, I am removing all this, okay? So, you understand the difference between Flutter and divergence, right? Flutter is associated with the vibration with increasing amplitude, and divergence is associated with increasing amplitude, but there is no, periodic solutions, right? What really happened here? We draw the, stability diagram. We plot omega n and we plot xi n basically, okay. So for any system, you can find out for any system when it results into quadratic eigenvalue problem, you can find out lambda k, and from there you can estimate omega k and xi k, and then you can plot as a function of the what is the controlling parameter. Here is the velocity, here is the velocity v, right? Wind speed, wind speed. So here you will see that what happened. So maybe you have multiple frequencies, you will have multiple frequencies. So all this one frequency started from here, one frequency start from here, one frequency start from here, and maybe these two frequency qualis, and then it goes. Then maybe after that these frequencies come and this qualis, after that this goes and this will go once again. Okay, after coalitions of these things they will come there. Okay, you see that how it is happening. Coalitions of this is indicated here, and then between these two, so this is the positive damping and this is negative damping. Okay, negative. So here they will go and then ultimately they will, here they will have this kind of circular kind of things, and then once again from here to here there is nothing. Okay, and once again from maybe these two will once again, then you see there's another flutter is happening over there. So here also there will be this kind of, you see that how the stability diagram with increasing C, the flutter is triggered by coalitions of these two modes, where the omega is basically coalescing. Then after that at some point of time this is bifurcating, and then if you drop it, project it on the damping axis, what is happening here, if you plot them, this will give you the like circular kind of stuff. Okay, and then once again it is once again bifurcating, then once again here, see, maybe if I denote this is the first mode, this is second mode, this is third mode, you see that, then it is the coalitions of the first and second mode which is triggering flutter here. You see that it's coalitions of first and second mode which is triggering flutter. This is the coalitions of the first and second mode. Clear? And then the coalition doesn't last much. Then what is happening? The mode 3 and mode 2 is coalescing here. You see that mode 2 and mode 3 is coalescing, and then they are going, and then they are once again bifurcating. That bifurcating is indicated by once again this is the circular things in the damping axis. Clear? And then once again maybe at later there can be further coalitions and bifurcation. So this is a stability diagram where we can see the variation of the frequency and variation of the effective damping as a function of the changing parameter. Which parameter? The parameter which is controlling the stability behavior. For this case it is the speed, wind speed, right? So I understand why the frequencies are coalescing and why they are bifurcating, okay, and why they are projecting, and there you can say this is a circular kind of things are coming, right? Clear? Please note that they are appearing in pair, complex conjugate, right? So when one of these will be a positive value, see, and but both are coalescing, but even though they are coalescing, one part of it has positive damping and the other is negative. That's why this kind of locus is given. And it can be a smaller size, it can be a larger size depending on the span of these coalitions and bifurcation. And if it is a small one, then this is called weak flutter. If it is a large one, this is called strong flutter. So please try to understand, weak flutter and strong flutter, weak flutter and strong flutter. What happens? You see that the one which is weak flutter, this weak flutter can be suppressed by increasing damping, some kind of damping, but the strong one is difficult to suppress. If you increase the damping by some artificial means, weak flutter can be eliminated, okay, but strong flutter cannot. So, this is the discussion essentially is we are concentrated around the aerodynamic stability of cable stayed or cable suspension bridge. Please note that other type of bridge are not susceptible to wind, okay, because they are too stiff. Cable suspension or cable stayed are flexible to have flutter, but what about girder bridge and other thing? There flutter generally does not manifest as a global failure mode. There might be localized flutter of some component and thing, that is a different thing, okay. So, that is why you will see steel bridges, which are steel girder bridge etc., they are not checked against flutter. Wind tunnel tests are generally conducted, mandatorily, mandatory to conduct wind tunnel test for the cable stayed and cable suspension, which has a larger span, and then because of the suspension cable and the load resisting system, they are flexible, inherently flexible. That is what is done, okay. But not only bridges, but these are also very important for aircraft wing and other structure also. It's a flutter is was very common mode of failure in aircraft structure. And now there was a whole branch of aeroelasticity for that. This not exactly flutter, but yeah, flutter also happens, and not only flutter, there are other kind of aerodynamic instability also happen in chimney, and chimneys also need to be tested for the aerodynamic instability. So, you once again you do the aeroelastic modeling for chimney and they put in the wind tunnel, and then you slowly increase the velocity, wind speed, and then you will see suddenly there is a huge jump in the vibration, okay, and then that basically that critical velocity is triggered as the velocity which is triggering flutter. So, you have to avoid that, and in design you want to push it through by modifying the geometry and things like that, or sometimes there is artificial means you just attach some kind of stack or structure around the chimney and things like that, which will break the vortex structure, okay. So, what happens in then for a chimney when the flows, see chimney there is a basic difference for bridges and chimney. Bridges are basically what? Streamline object, but chimneys are bluff of body. So, airflow is incoming airflow, it got stuck, there is a technician joint, and at the end downstream there is vortex heading, and because of the vortex heading it is not the along wind component, but across wind component is more important. There is a huge vigorous vibration across the wind and transverse vibration, those are across wind. So, in the code you will see that there is a huge discussion on across wind and along wind, and then there are how much shear force is going to come. So, when you design, after that you have to do little check that how much shear force is coming from the wind tunnel test and how much is coming from your design value, okay. And also you have to identify that what is the critical load for the flutter, okay. Not only flutter, there are other kind of things happens also, which are called buffeting and also overhauling and other kind of instability, okay. But please note that essentially these are the basic formalism for analysis of dynamic stability, okay. I will now consider another case which is a little uncommon and not that much important for us from the, but this is called noise stabilization of system, noise stabilization of a system. What is that? I will give you a simple example, okay. You see this stick, right? If I put this stick, it is falling, right? But not falling, right? Why? Changing the, yes, that is what. So, it is an inverted pendulum system. So, I will get an example of inverted pendulum, okay. So, this example, just consider, this is the base, massless base, okay. The massless base, and then there is this rigid, and then the top of that there is a mass m, right? And this fellow, this base, whatever this base is, right? this base is subjected to some kind of vertical acceleration, right? And these I am considering for simplification, this we are considering to be rigid, okay, rigid, and mass is concentrated here. So then, I mean, this is not exactly fixed, so it can rotate. So I am considering it its degrees of freedom as theta. Essentially, when I am trying to stabilize it, this fellow is going to fall. Why? Because weight, if you perturb it, then component of weight is basically destabilizing it, because it is, but as soon as I am trying to, I am essentially with my hand, I am trying to put a vertical motion to this, okay. So when it is trying to fall, it is lateral disturbance, right? It is trying to vibrate in this plane. That vibration I am going to stabilize with vertical thing. See, when it try to fall, right, I am lowering down my hand, and when it is trying to come, then I am just taking it, So through my hand I am applying nothing but noise, you see. Why that is called noise? Because whatever I am applying is a much higher frequency than the frequency by which it is falling. That is what I am terming, the whatever excitation I am giving by my hand as noise. You see that? And this kind of stabilization is called noise stabilization. This is example, not only this might be a simple example, but that can also be utilized. Sometimes you see when the structures are subjected to earthquake excitation, especially vertical excitation. Okay. So both type of excitation, horizontal as well as vertical. So consider a system which is behave like inverted pendulum. Consider a water tank where there is a huge mass stage, is supported on by staging, right? And then it is lateral excitation is coming, but then at the same time vertical excitation is also coming. Then what will be the behavior of this? And vertical excitation is taken how much? 2/3, right, of the horizontal, right? Can have combination of recorded ground motion acceleration. So all of you are doing earthquake engineering, right? So you know that there can be 3 components, right? North, south, east, west, and then the vertical one, right? So when we are trying to analyze this by a very simple example, so when we do bicycling, right, we ride a bicycle, what kind of system is this? This is nothing but a noise stabilization. A baby cannot walk, but the human can walk, right? You see that? So all of these, I mean, some form or other, these are some example of noise stabilization. It is very important in physics, very different kind of system, classical system and others, there are systems in physics which uses this noise stabilization, is effectively utilize the noise stabilization of system, okay. So it has, other than practical application, it has, physical, I mean, this physics is very interesting, okay. I am assuming that this is excited by A cosine on omega t, right. The length of this length of this is L, and I am considering that A basically A is very, very smaller than L, right, okay. And well, I mean, then if you write down the equation of motion, write down the equation of motion, and you can, of course, the better thing is that we use the Hamiltonian Lagrangian formalism to for the writing down the equation. So for Lagrangian, if we define this to be origin, this I can take as x and this I can take as y, then how we will define the x and y coordinate? X and y, capital X and capital Y to be what? L sin theta, this is L sin theta is x, L sin theta, and y is how much? L sin theta plus y cosine theta whatever, right? L cosine theta plus y is the vertical deflection that you are going to give, y is equal to, right, we have taken it y is equal to a cosine omega t, right, y plus L cos theta, right, fine. So then what is x dot? X dot is L cosine of theta into theta dot, right, and y dot time derivative is L minus sine theta dot plus y dot, right. So, we calculate velocity square is nothing but x dot square plus y dot square. You have to calculate velocity because when you apply the principle, Lagrangian is what? Lagrangian is kinetic energy minus what? Potential energy, right? Lagrangian, huh? So, x dot plus y dot. So, here you will get, if you simplify, you will get L square theta dot square plus y dot square minus 2 L y dot theta dot sin theta, and when I am writing Lagrangian, so half m v square, half m v square means this one, L square theta dot square plus y dot square minus 2 L y dot theta dot sin theta minus you see that potential energy is nothing but mg and then vertical displacement, right. So, mg m into g y plus L sin theta, right, y plus L cosine of theta, right. So, this is the half mv square kinetic energy minus the potential energy is the weight multiplied with these things, okay. So, then you write down for the equation of motion, what is the Lagrangian equation? Equation of motion is nothing but ddt of del L del theta dot minus del L del theta is equal to 0. We are not considering, I mean external excitation we are not considering, this is the, damping etc. Non-conservative force we are not considering, okay. There can be damping and other things, but that thing we are not considering, right. So, if you just do it, then you will see that the way you will get this from here, you will get the equation of motion to be L theta double dot minus y double dot sin theta is equal to g sin theta, okay. And then if you substitute L theta double dot minus y double dot sin theta g sin theta. Now, you substitute y is equal to what? Y is nothing but a cos omega t, right. So, y double dot is nothing but minus a omega square cosine of omega t, and that if you substitute, you will get ultimately by simplifying, theta double dot plus sin theta divided by a omega square cosine of omega t divided by L minus this, you just put it in length L, okay, length small l, a omega square cos omega t L minus g upon L is equal to 0, okay. So, I will just remove the top portion, and I will finally see the equation of motion, and then we will see that what is going on. So, ultimately the equation of motion, what we theta double dot plus sin theta, and here it is minus g by L, plus a omega square cosine of omega t by L is equal to 0. So, you see here, if you consider the pendulum, I mean, you can recall if it was the equation of a pendulum, then G by L is basically the frequency, right, isn't it? So, we can effectively what is happening? Effectively, you see that when we are exerting a vertical excitation from the base, which is amplitude is a cosine omega t, but effective acceleration is minus a omega square cosine of omega t. This acceleration is counteracting the gravitational acceleration. So, effective acceleration that is coming is like this, and which is a function of nothing but this excitation frequency omega t, right, fine. So it's a reduced acceleration. If you can recall omega 0, omega 0 is nothing but root g by L, right? If you can recall, for the frequency of the pendulum is how much? Root g, L by g na time period. So omega 0 is root g by L, right? Omega 0 square, right? Here I will introduce some dimensionless quantity, okay. I will introduce omega 0 is root g by L, and I will write small a is equal to capital A divided by normalizing. So these are dimensionless quantity, okay, for simplifying the analysis, okay. So then if we do, then ultimately this equation simplifies to theta double dot plus theta a omega square plus omega t minus omega 0 square to be 0. So this is the ultimate equation. So what we see here, that now we will see the interplay between omega 0 and omega. So we know that if omega is large enough, the stick will not fall, right? The stick will not fall. That means omega is much greater than omega 0, and because omega is much greater than E0, so omega, if omega 0 like it, omega 0 looks like this, and omega dot will look like like this, huh? You see what I am trying to say. So the slow cycle one is omega 0, right, and omega is the this kiss, right. So that's what omega is termed as noise. You see that, because that is a much higher frequency. That's what omega, we can write, what is noise and what is signal, right? Okay. And another thing, this phenomena we have to explain analytically. So we can solve the equation by substituting. We can adapt various value of g, L, and for different value of omega, okay. I will show you the behavior with time with two different value of omega, okay. This is for omega is equal to 10 per second, and this one for the another case it is this is for omega is equal to 100 per second. You see that the difference. See, for one case it is diverging in one, but in other case it is trying to go, and whenever it is trying to diverge, the noise is stabilizing it. So and it is compatible to the fact that is omega is very large, then the stick will not fall, right. So we can do little analysis and then we can see. So I will not go into very much details, but basic thing I will just show it. So let us take theta t. We want to find a solution of theta t as some c plus b cosine of omega t. You can see c plus b cosine of omega t. B is the amplitude of the small capital omega, and c is basically, c is also a function of t, okay. We can assume this kind of solution, okay. C is the small slow cycles, and then omega is the one which is basically modulating it, okay, fine. So then we can, what we can write, and what we can write, that small b, we can see that b is much more smaller than c. B will be much more smaller than c. That is very simple, because c is the slow oscillation, and b is basically is riding on that. So that's what b much smaller than c, that is justified, right. And another thing, c basically c changes in time scale, of 1 by omega. Okay. So 1 by omega means, see, high frequency will change, but silly, omega is very high. So 1 by omega is small, right? So that's what C is slowly changing. That means, this means it is slowly changing or changing slowly. Huh? So then, that is the kind of solution that we see. Of course, this is a function of t. Please note that. Huh? It is C is a function of t. Huh? Please. Huh? Now, if you substitute thing, substituting in the equation, then we will get, minus b omega square cosine omega t plus C a omega square cosine of omega t is equal to 0. And if we find the leading order term, so from there what we obtain is that small b is equal to small a into capital C. Okay. Small a is a small number, right? So from there we can write that theta, the function of t, is nothing but C 1 plus a cosine of omega t, right? By substituting, because C is basically, b is nothing but a into C. So C into 1 plus a cos omega t. Huh? So we will see that how C changes with time. Okay, we will see that how C changes with time. C changes with time. So we will try to find out the average acceleration. So when I am putting a bar, that means it is average. You understand that, right? In statistics, we put a bar to find out the mean, right? So we average over a cycle. So theta double dot, I am just putting minus theta a omega square cosine of omega t minus omega 0 square, and this is equal to minus C a plus a cos omega t a omega square cosine omega t minus omega 0 square. There is also there is a bar, okay, and then it will be nothing but minus C. If you just substitute it here, a square omega square bar cos square omega t minus omega 0 square, and from there this is minus C. Now cos square omega t, if you just sum it up, okay, the average of cos square omega t taking us to be 1, okay. If you integrate it over a cycle, right, integration of cos square omega t, then you understand what I am trying to do, right? Bar means I am integrating this over a cycle, complete cycle, okay. Over a complete cycle I am integrating it, then you will get a square omega square divided by 2 minus omega 0 square, and that means it's nothing but minus capital C capital omega square. So from here what we see that the motion will be theta double dot plus C omega square is equal to 0, where capital omega is nothing but root a square omega square by 2 minus g by L. And from here what we write is that, so theta double dot bar, this is nothing but equal, this is same as basically C double dot, right? This theta double dot bar is S as C. So this we can write at C double dot C plus capital omega square C t is equal to 0. That is basically the equation for the slowly varying component. Okay, so this is the equation for the slowly varying component. Okay, which is on which the high frequencies are ridden. Okay, so the slowly varying component oscillate at a frequency of capital omega. So slowly varying component. So the C, oscillates with frequency omega, right? And that is nothing but, and how omega is defined? Omega is nothing but, this is nothing but root a square omega square upon 2 minus omega 0 square. Okay. Now here you see, from here you can clearly get the condition. See, when omega will have some value, if a square omega square 2 is greater than omega 0, right? Isn't it? So for stability, you see that from here, what you see that for stability, this must be greater than 0, and that is only possible when a square omega square by 2 must be greater than omega 0 square. That means, a omega by 2 is greater than omega 0 root 2, or omega is greater than root 2 omega 0 by a. Now what is A? A is nothing but what? A is what? Capital A by L, right? So capital A by L, L is much greater than A. So A is anyway a small quantity, right? A is anyway a small quantity. So what is the excitation frequency that you should apply from the below? That should be much greater than whatever is the slowly varying frequency by root A. That means these conditions must be satisfied. Then only the system will be stabilized. So this is the condition of stability. And from here, what we can say that, so essentially what is happening that, see, omega 0 is the frequency for the slowly varying component. If the system will be stabilized, if the, the noise that you are putting as an excitation, that is much greater than C. A is a small quantity, right? So that is much greater than omega 0. See, omega 0 divided by small a is a small quantity. So you see that omega, it will be even further, increase this thing, you see that. So if you remove this A, then what will be the, if omega is greater than root 2 omega 0, that means this clearly you can see that omega has to be much greater than omega 0. You see that? Because A is a small quantity, right? Clear? So that is the condition needed. So qualitatively, if you want to say, that means, your vertical excitation should be large enough, frequency should be large enough, so that it basically prevents its lateral, is falling it laterally. Okay. And because it is so high, and so high means what? You see that? So slowly varying component, that means here basically the C. B is much smaller than C. So B cos omega t thinks is nothing but this small term, this one. Omega is much greater than 0, that is, you can see this, so its amplitude B. So if this amplitude is basically a small amplitude, and this frequency is capital omega, and this capital C is basically the amplitude for the whole thing, right? So what is happening when it is trying to destabilize, this high frequency is basically stabilizing it by overriding to the slowly varying component. Similarly, it is going to be, see, if it is diverged like this, then it is going to be unstable. But the high frequencies, it is stabilizing it by bringing it to this level, right? And so on. So it is allowing the system to be stable. So you understand the noise stabilization. The statement that I have given is not by no means comprehensive, but this is a very simple example, very simple and ad hoc way to explain to you. But nevertheless, you have understood that why it is called noise stabilization. It is, we are calling it noise because this is a very high frequency comparing the slowly anything with very high frequency, a slow amplitude is termed as noise comparing the main signal. So, the main response is there on the slowly varying component. On the top of that, this noise is riding high frequency, small amplitude. Okay, this is noise stabilization. Okay. So, thank you very much for today's class. In next class, we will cover little more on dynamics in stability. I will introduce to the concept of a life on of stability, but there are many things. See, entire class can be devoted to dynamic instability. So much stuff is there, okay, and they not only civil engineering system, but fluidic system, this system, that system is there. We don't want to bore you with that. So, next class we will do little bit and then we will go to the last chapter, that is on boggling of cell. Okay. Thank you very much for today's class.